Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, I want to welcome Fredo Durand here today to visit us. So I know Fredo, I think I met him first when I was an intern at Merle, and I used to go over to MIT and hang out with his group and do paper readings. That was about a little over 10 years ago. Fredo has been one of the pioneers in computational photography and helped launch the first symposium in computational photography and the first conference. Now, they're known as ICCP, and there have been 6 or 7 since, something like that, maybe more. Fredo has done a lot of seminal work in the area. We're really happy to have him here with us today, so I'll turn it over to Fredo. Thanks.
Thank you, Neil. Thanks, everyone. Always a pleasure to be here. I'm going to give somewhat of a potpourri talk with a lot of different things, and the end will be a little more coherent. Because my research group does a lot of different things, including computational photography, as Neil said, but also some good old lighting simulation. And recently, we've been interested in content creation in the area of education. And also, we're getting interested in the use of computer graphics simulation for robotics and vision. We don't have any results yet, but I'll be happy to chat about potential and excitement. So today I would like to first advertise Halide, which is a compiler that we created in my group for high-performance image processing. So who has heard of Halide here? Okay, some people who's written Halide code. Not that many people. Well, I have. So for those who don't know, so Halide is a language and a compiler to help you write very high-performance image processing code. If you've never tried to optimize image processing applications, it's a lot harder than it seems. It's not just writing a few assembly lines in the inner loop. You've got to take parallelism into account, get good cache coherence. And cache coherence is really the thing that makes it hard, because typically in image processing, you do a pipeline of operations, this blur, that curve thing, that color stuff, a little bit of denoising. And if you don't pay attention, by the time you finished one operation and start doing the next operation, all your information is out of the cache, and so you need to get it back from main memory. So the game is all about trying to merge functions and try to work on little tiles of an image. But it's hard to know which functions you should merge because you need to also expand the tiles. If you do a blur, you need a little information at the boundary. So there's a lot of complexity that goes into this. And furthermore, these days, people want to have their code run not only on their desktop, but also on their mobile phones, on the GPU. And optimizing for these different platforms is hard and typically requires people to rewrite code from scratch. So let me show you a quick example for what I mean. Here's a very simple 3x3 blur that's done in 2 passes. First, a horizontal blur, I believe, 3-tap, and then a vertical blur. And so the combination gives you a nice box filter. And so you get a nice for loops, for y for x, for y for x. And the problem with this organization, as I said earlier, is by the time you start computing your vertical blur, the information in your upper left corner from the horizontal blur is far gone from the cache, and you get a lot of cache misses and things go slow. So if you want to optimize this code, so this is what it starts looking. So this is hand-optimized C++. There's a lot of dirty stuff. There are a lot more for loops. Now you see that things are 4 level deep instead of 2. That's because of the tile organization. You've got a lot of craziness for the indices. So now things don't go from 0 to something. They go from -1 to 32 plus 1 because you need to expand stuff. There's a lot of dirty vector instructions and all this. And the only thing that's easy in this case is the parallelism. That's the green thing up there, the multi-core parallelism. And importantly, in doing this, we really had to merge the 2 stages of the blur and do a lot of thinking about how to reorganize the computation. And this is only for a two-stage pipeline. So you can imagine if you have a whole photography application, you've got a lot of mess, and you really need to not only optimize individual pieces, but optimize the combination of the pieces. And in particular, you can't just rely on a fast library like, Intel has a really good image processing library. Each individual component is really hard to beat. But then when you put them together, you lose optimality because of cache coherence. And so with Halide, you can do exactly the same thing that we did here, but with this code. And one of the key ideas is to separate the algorithm, which says what you want to compute, from what we call the schedule, which deals with all this reorganization of computation and all this optimization. So it's a functional language, so we don't even have loops in the language. You just say, your formulas for the horizontal blur, formula for the vertical blur. And then there's a core language that tells the compiler how to organize everything. So for example, here we say, OK, we're going to compute the vertical blur in tiles of size 256 by 32. We're going to vectorize across the inner dimension in strides of 8. We're going to parallelize for the multi-core architectures using the outermost tile coordinate. And then the first blur, the horizontal blur, we're going to compute it at the granularity of the tiles of the output blur. And we're also going to vectorize, because vectorization is good. And so this code produces exactly the same executable as the previous C++ code. And hopefully you'll agree that this is a lot cleaner and a lot more manageable. And in particular, you don't need to touch your algorithms. They stay really clean. The algorithm can be written by somebody else than the person who does the optimization. When we wrote the paper, we kind of mentioned this as a possibility without fully believing in it. In practice, that happens to be the way it's most used. So some people write the algorithm, and then you have 2 or 3 gurus who do the optimization. And just a little bit of bragging, so it's still old. We did some tests with one of the functions of Adobe Lightroom. If you use either Lightroom or Photoshop, there's this highlight and shadow and clarity that rely on a technique that Sylvain Paris and others developed called local Laplacian filter. It's a fairly complex pyramid processing operation. I don't remember how many kernels we have. It's like tens of kernels. And the person who wrote it for Adobe, he's one of their best programmers. He took the reference C++ code that he had, and he was able to get a factor of 10x. But that took him 3 months of work. Partially because he had to try different acceleration strategies, different reorganization, and each time you do a reorganization, you really have to rewrite the whole code from scratch, essentially. And after trying a few times, he decided that the last one was going to be the one, because he didn't have time to work on it. And then my student, Jonathan Reagan Kelly, who created Halide, went at Adobe for an internship, and he took 1 day to rewrite the same thing in Halide. And in 1 day, he got code that was twice as fast as the original, as the heavily optimized Adobe code. And with another hour, he had code running on the GPU that was another factor of 3.5 times faster. So you really get huge productivity gains with this language. And so if you do any image processing and you care about performance, I really encourage you to look into it. So we presented Halide a few years ago now. And since then, it's really turned into a more industrial strength compiler. In particular, the people at Google have been adopting it seriously and have been contributing back to the open source compiler, so that now it has a lot more features that make it usable in many scenarios. It can compile to x86, to ARM, to even MIPS, various forms of GPUs. As I showed, it's really fast and really concise. I mean, some of the recent results we have a matrix multiply that's faster than Eigen. We can do Gaussian blur faster than the Intel performance primitive. And we can do FFT faster than FFTW. And as I said, so Google uses it a lot. All the Google photo code runs with Halide, at least all the image enhancement. The HDR Plus mode on Android runs with Halide. And YouTube now uses Halide, I think, for the denoising thing. And I've been told that essentially the CPU time they save by running their denoising with Halide is enough to pay for all of Mark Lavoie's research team, because YouTube ingests so much data. So there's really a big gain in performance. And of course, this is something that you could do all this by hand. It's not like, it's all Turing complete, except you'll do it way, way faster with Halide, and you'll be able to explore more optimization strategies, which makes it much more likely that you'll find something close to optimal. And some of the new things in Halide and some of the soon new thing, hopefully, there's more parallel reductions. It can now handle some form of sparsity if your arrays have some areas that are empty. The thing that's maybe more important is that, so there was a paper by a team from CMU and Stanford, where my former student Jonathan Reagan-Kelly went, that developed a technique that can do all the scheduling business automatically. So far, you still had to write these instructions about what to tile, what to merge, and all this. Now with this new technique, they can do it automatically. There's a branch that you can already download from GitHub that allows you to do this. It's not part of the main branch, but hopefully within the next 6 months, it will be added to the main branch. And that will make things a lot easier, because doing the right scheduling still takes some amount of expertise. And the folks at Google are also working on a library of standard image processing with Halide, so that you don't have to rewrite Gaussian blur and all these things, etc. Oh, interesting. Keynote did some interesting autocorrect. We're not doing some auto-dialing. We're thinking about adding some automatic differentiation, not dialing. So computing derivatives automatically, but this is still very speculative, nothing concrete is happening, which could make it very useful for things like deep learning, where you like to play with derivatives and backpropagation. But this is really not done yet. So that's the advertisement I wanted to make for Halide. As I said, really, if you care about image processing performance at this point, this is by far the best development platform. It works on Windows, it works on Mac, it works on Linux. It's really versatile. All right. As I said, this talk is going to be a little bit of a mix of different things. You may have heard about our work on video magnification, so I'll just very quickly summarize the basic idea. So in general, we're very interested in using computation to reveal things that are invisible to the naked eye. And with video magnification, what we do is we take videos where it looks like nothing is happening. So, and I'm going to have too many clicks needed. Okay, so all these videos are playing, I think. It looks like nothing's happening, but there are very subtle things happening. And what we can do is, through computation, analyze these temporal changes, magnify them, and visualize them in new videos where, so let's see. All right, so now you can see that the redness of this face is changing with each heartbeat. You can see how this crane is swaying in the wind. You can really see the chest movement when this baby is breathing. This is an SLR in the vibration where the mirror lifts up. And all these movements were in the original videos, but they're really tiny, maybe 1 pixel, maybe even 1/10 of a pixel. We've extracted movements as small as 1/100th of a pixel, and we can make them visible and help people understand what's happening in the world. If you've looked at the original papers, I still encourage you to have a look at our upcoming communications of the ACM version. I think we do a much better job at explaining what's going on. One of the beauty of this line of research is that the algorithms are very, very simple. I think that in the CACM paper, we explain better why such simple solutions do work. One of the key arguments is when everything is very small, anything linear works because of Taylor. And so all the stuff that shouldn't work when you're dealing with big motions all of a sudden start working because things are too small that linear is good. And we also, I think, have a better explanation of what we do with those complex valued wavelets. Recently, we've been pushing applications of this technology, which required some more development. In particular, one big question when you do things like this is what I am seeing real? You know, we do all this processing and filtering this, filtering that, and you know, if you take random noise and you do enough shaping of it, it's going to look like something is happening. And we've spent a lot of our research meetings wondering, is this thing really moving the way it does? It seems to be. And finally, we did some noise analysis that tells us, you know, we understand if we have some input static video or slightly moving video, and there's some camera noise to it, when we apply these magnification algorithms, this is by how much ghost motion we may see. We did both some pen and paper math derivation and some Monte Carlo simulation, and now we have a good sense of the signal to noise that we get with this technique, which is very important for quantitative applications. And we even have a real-time halide version because we eat our own dog food sometimes. And we've been pushing applications to civil engineering. We have collaborators in the Department of Civil Engineering. We've been looking at various structures. This is an example of a bridge in New Hampshire. We took a video from the shore, and this is just from the ambient motion, from the cars, etc. We can really show what's happening. And from the same video, using different temporal filtering, so this was, if we amplify the movements around 1.7 hertz, but if we amplify movements around, and I'm going to get my numbers wrong, around 2.5 hertz, now we get a different mode of variation, and you see all this torsion of the bridge. So this is one of the advantages in mechanical engineering. Because we have this ability to temporally filter things, we can really extract different modes of vibration. And our collaborators have been doing things like trying to use these small motions to identify changes in behavior of the structure. You know, if you remove a bolt, do things start moving differently? What if it's a little broken, a little rusted? Or detect that there's a passage of a truck and things like this. Yes?
400 means the play speed, or
400 is the magnification. So the original motion was 400 times smaller. Yeah, so and then it's really just spatial extent. So, you know, if it's moving by this, it was moving by 400 times less. Yes?
Did you verify that motion, like through some other sensors?
Yes, so we did a bunch of verifications. We did some comparison to laser vibrometers, to accelerometers. One of the funny things is that, so essentially the three technologies that you may want to use to measure these small motions are accelerometers, laser vibrometers, and video-based stuff. And you get different orders of derivative. So the accelerometer gives you the second derivative of the movement, the laser gives you the first derivative, and we get the actual measurement. And so you get different pros and cons depending on the frequencies you're interested in. Yeah. But one of the big advantages compared to accelerometer, of course, is that you don't need to stick a sensor to the structure. And even the laser vibrometer has its limitations. You usually get a point measurement unless you use a scanning version, and you have some restrictions in terms of the reflectance of what you're measuring. Another class of applications is biological systems and the human body. This is work by collaborators who study the eardrum. And I don't fully understand the biology or the anatomy, but essentially they're studying the vibration modes of these tectorial membranes that vibrate with sound, which eventually gets turned into a neural signal. And they're telling us that using our technology helped them discover a new mode of vibration for this membrane. And it helped them in two ways. First of all, so what they do is they take a piece of this membrane, they put it under a microscope, they put some piezo stimulation, and they see how things move. And they had some technology to help them with this, in particular some traditional, essentially vision tracking that takes a point and gives you a 1D plot of how this point evolves over time. And our visualization helped them in two ways. First, it helped them see if there was a problem with the sample they were studying. Half of the time they would tear the membrane or something bad happened and the motion was completely unusable. And with their 1D plots, it was hard to tell if this was the case or if they really were looking at real signal. Whereas with our visualization, they would say, oh yeah, there's a problem here. We can see what's going on. And they're also saying that in order to understand this new mode of vibration, it was a lot easier cognitively to just look at the video and see how the wave was evolving rather than trying to infer it from a bunch of one-dimensional plots that are not as meaningful. And in general, this is where this kind of technology is really useful, that it allows you to see a dense spatial representation of the movement, and our visual system is really good at interpreting this kind of visual information. And we're also pushing other applications with people in medicine. We've started working with people who study Parkinson's disease and things like this, where small and not so small human shaking and vibrations are important. The other thing we did with this technology is to use those small motions to create new videos of a structure. So we came up with these interactive dynamic videos where we can observe how a given object moves or vibrates, extract its vibration modes, and use them in order to generate new animations. So we capture a little video. Am I playing? Yes. We see how it moves, extract the various modes, and then we can synthesize new videos as linear combinations of the vibration modes that we extracted. So you're going to see this on the right, hopefully, maybe. Yes. So we can pull the thing and it can deform realistically, which is very similar to what people used to do in graphics with 3D simulation, where they would simulate things a lot to pre-compute all these vibration modes and then create new animations in real time. But we can do the same thing, but from video rather than requiring you to do an actual simulation. We're also interested in the comparison of motion. So far, we are only focused on motion being small everywhere, but you also have cases where you have large motions that are very similar, but the subtle differences can make a big difference. So these are two different videos. In one case, he made it, and in the other case, it was a fail. And so it may be very interesting to study what's different about these two things. But side-by-side videos are really hard to analyze. And in fact, people who work in computer animation told me that sometimes they get the problem that they show side-by-side comparisons between previous work and their work, and reviewers say, I can't see the difference. It's just too hard to go back and forth. And so I think there are lots of situations where you have these similar videos that you want to compare. And so far, we don't have good tools for this. And so we started developing some visualizations to help people. One method we developed is this combination of one video plus the edges of the other video superimposed so that you can compare things in the same frame. And we do some color coding when things seem to be very different. So the red areas are where things are very different. So we still rely on the human visual system to do the analysis, but we feel that and we have a user study backing this up, that by putting everything into the same video and doing this clear separation between one video that's shown as a video and the other one that's shown as edges, people have a much easier time telling the differences. We've done some work on seeing through walls using Wi-Fi in collaboration with Dina Katabi and Fadel Adib, who are Wi-Fi people. So this is a little Wi-Fi antenna, and with it we can reconstruct a very coarse version of the human body on the other side. And this is essentially radar technology, except using Wi-Fi waves. And the whole challenge is that just like with radar, you only get a reflection when things are in the mirror configuration. And so you have to do some reconstruction over time in order to know where the various body parts are. We're interested in systems issues, so halide was one example. As I'll say later, I think there's a lot more work that needs to be done with systems issues in computational imaging. In particular, I got tired of everyone telling me, oh, if you've got an algorithm that's too slow to run on your mobile device, it's very easy, you just run it in the cloud, and then you get infinite computation capability, and things are fine. Except, of course, the big problem with running things in the cloud is that the transfer of information is really costly. And this is essentially the same story as with halide and cache coherence, except with a different scale. Transmitting data from the main memory to the processor or from your mobile device to the cloud is a really, really costly operation, both in terms of time and power. And so in many situations, I mean, you really need your algorithm to be very, very slow in order for cloud computing to be a worthy alternative. And with Michael Garby, Sylvain Paris, and a bunch of other people, we developed one solution in the case where you do image enhancement and you don't have spatial transformations of your image. And we have this way to compress not just the input and output of your image processing application, but what we compress is actually the transformation from the input to the output. And because in image enhancement, the input and the output tend to be very similar, this is a lot easier to compress. And also it allows us to work with a really bad quality version of the input. And still, you know, if you apply the algorithm you wanted to apply to a bad quality of the input, get a bad quality output, the transformation between these two bad versions is still relevant for the good quality version of the image. And we saw some big gains in transfer. Quick flashing of various recent stuff. We just got conditionally accepted to SIGGRAPH Asia. Of course, we had to jump on the deep learning bandwagon like everybody else. And we worked on demosaicing and denoising, and we claim much better results than previous techniques like Flex ISP. You see all these artifacts that happen here, all gone from our method. So this is Adobe Camera Raw, this is our stuff, and similarly for this one, we really get rid of more artifacts. As usual with deep learning, the trick is not the network itself. We use something fairly standard. Of course, we tried to be innovative and then concluded that this didn't matter. The main issue is how to get data that addresses your problem. In the case of denoising and demosaicing, the challenge is that the problem is easy most of the time, except when it's not, and when it is, then you get really bad artifact. And these are examples, you know, most of this is very easy, and that's what you get in most of your image data sets. Stuff like this, much harder, stuff like this, much harder, but it doesn't occur often enough that a normal data set will do it. So we had to develop some techniques to mine for the hard examples and in order to learn effectively. Another recently accepted paper is work on bounce flash photography. So I'm a big fan of bounce flash, as you probably know. If you use the flash for direct lighting, things don't look that well. That's why people usually hate the flash. So good photographers, what they do is that they turn the flash towards a wall or the ceiling in order to get better illumination. The problem is that choosing in which direction to bounce the flash is not so easy. And especially if you're moving and your subject is moving, you may have to reassess all the time. And so we came up with a computational and actuated solution. So we put a flash on a bunch of servos so that the flash can rotate automatically. And with some 3D sensors and a fisheye, we automatically assess in which direction you should go, also taking into account the pose of the subject, if the subject is looking left or right. And we can fairly reliably get good lighting with bounce flash photography. And maybe the two main ideas I'm very excited. Well, the three main ideas I think that are worthwhile here is, first of all, this idea of using indirect lighting really gives you a lot more flexibility. You know, even though your light source is on the camera, your virtual light source is somewhere else, so that's really powerful. Doing photography with awareness of your whole surrounding is also very powerful, and I hope that, especially due to demand in robotics, we'll start having more hemispherical sensors that give you information about the whole environment, including 3D information. And I think also that there's a lot of exciting things to do with actuated photography. When you start moving lights, moving the camera with robotic system, a lot of fun things can happen. And this is an example of the system in action in the hallway. So we're moving, the subject is moving, and you see that as some bad reflectors arrive on one side, the flash is going to turn the other way to give you a good bounce flash. And essentially, everything we do, a professional photographer could do as well, maybe better, but they'd have to think about it all the time. And also, we want to bring it more to the masses. I mean, we're very inspired by things like autofocus. Some people still do manual focus, not that many people, and it's really helped a much broader range of photographers achieve good images. All right. And we still do some lighting simulation, as I said. I wanted to flash this title because it's my title with the highest number of mathematicians in it. And I'm a little sad because even though we use Taylor expansions, we don't have Taylor in the title. But this addresses the good old problem of integrating indirect light. And the big problem we have, all the easy things have been done. Now, the problem is that, especially when you start having shiny surfaces, we're trying to compute this integral in this fairly high dimensional space. And the space essentially can be parameterized by, say, XYZ coordinates of each point where light bounces. So, light goes from this light, maybe here, bounces, and so with each bounce, you get 3 more coordinates. And unfortunately, especially with specular surfaces, a large part of this space is not very useful, and only a very narrow part actually contributes to light. And it's so narrow that it essentially has volume 0, so it's really hard to sample and find. And so we came up with a technique that uses automatic derivatives to help with the sampling. So at a given path, we compute the second derivative, so both the gradient and the Hessian of the lighting contribution, so that we know in a neighborhood in which directions there's good contribution or not. And we also use ideas from Hamiltonian dynamics in order to sample from this information. And this allows us to get much better results. And also, surprisingly, it makes metropolis light transport, which traditionally has been a very, very hard algorithm to implement, much easier to implement because the second derivative trick takes care of doing smart things, so you don't need to hack until you have good sampling strategies. And in particular, it allowed us to develop the first metropolis light sampler that works well with the temporal domain. So far, as far as I know, there's essentially only one implementation of metropolis light transport that's available out there, and maybe another 10 that people have been able to complete. It's really hard. It's a very simple algorithm in principle and very hard to implement in practice. So I think it's quite an achievement that my student was able to not only get a metropolis light sampler to work, but also extend it to the temporal domain, with just 1 extra week of implementation. And this is in part because we use derivatives and we use automatic derivatives. So, if we add the temporal dimension, just the compiler will do the job and will compute the derivatives for us. We don't have to rederive anything or change our strategy. It's going to happen automatically. I've become a big fan of automatic differentiation. It's a really cool tool. I highly recommend it. All right, so this was a very broad, disconnected overview of some of the recent stuff we've done in my group. And to keep the talk even more disconnected, I'll now broaden the discussion and try to offer some thoughts I've had about the field of computational photography. I've recently had a chance to give a very general, broad talk, so that's what I decided to talk about. So as most of you probably know, computational photography is based on the idea that computation has a central role in image formation. So that is, the pixels we get are not just an optical projection of light onto a sensor. They underwent a lot of deep calculation, which allows us to gather visual information that would be difficult, if not impossible, through optics alone. And I think it's a very exciting field to work in, partially because it's so interdisciplinary. There's a lot of math, physics, optics, algorithms, theory, but also art, human visual perception, and all this. And if you like computational photography, I encourage you to have a look at my blog called The Computational Photographer, where I've been trying to centralize some of my thoughts about the field and some reactions to recent technology development. Now, thinking about the state of computational photography, I mean, first of all, the good news is that the field has had a lot of great successes. If you look at the camera pipeline today, it's fundamentally computational, starting with demosaicing, denoising, and ending with compression. So really, photography today is very computational. And every single phone or camera that you get will have things like panorama stitching or high dynamic range tone mapping. Maybe less known, although probably more known in this room, you have more and more cameras and software that use computation to correct for optical aberrations. In particular, radial distortion and vignetting are very common. So, you know, if your straight lines are not straight due to the optics, computation will fix it. But also chromatic aberration and even blur in some cases. And this is really changing the way people design cameras and lenses because they know computation is going to fix these problems, so they don't have to work as much on them and they can focus on other stuff or reduce the costs. And other successes include phase detection, video stabilization to some extent, gradient editing, patch match, and a bunch of warps. On the other hand, some ideas that have created a lot of excitement in the SIGGRAPH and computational photography community, I think haven't had as much impact as we would like. And I want to talk about computational optics, things like coded aperture that I worked on, flash, no flash photography that UXI and others have proposed, haven't really happened in the real world. Light fields, despite Lightroom's best efforts, still are not as much a reality as I'd like. And there's a little bit of deblurring in Photoshop, but a lot of the work we've had on blind deconvolution hasn't had the impact that we would like. And I'm not saying that these are bad ideas. I mean, I'm still very excited about a number of these ideas, but I think it's a combination of just it takes time for ideas to make it, for the technology and the market to be ready. I think some of these ideas we haven't pushed enough, and I think some of these ideas we should also think about applying to different problems than just photography itself, and I'll get back to this. But I think that the community has to keep pushing and also keep having a reality check, trying to understand why this is not happening yet. And vice versa, I feel that a lot of basic camera functions are still open technical problems. If you look at white balance, automatic white balance, especially with mixed lighting, it's still not working as far as I'm concerned. Autofocus is still not great, especially for video, and the same goes for auto exposure. And the user interface of most cameras is still a disaster. Depending on the camera, not always the physical button layout, but the logic of the UI and what you control and how you control it is really not where it should be. And I think one fundamental problem that we have is that the field of computational photography doesn't have enough synergy with industry. I think that some companies, and in particular Adobe and Google, are doing great at doing very good research and very good transfer. I think that cell phones have been a great open platform for computational imaging. Microsoft Pix is one example of this. But of course, the big problem is that traditional camera manufacturers really have been extremely reluctant at thinking computationally. I think they're fundamentally hardware companies, and they just cannot embrace computational thinking. And it's super frustrating. It's 2016, my big DSLR is still not programmable. 20 years ago, we had DSLRs that were programmable, not anymore. This is completely crazy. I mean, I can do computational photography on my cell phone that I can't do on my multi-$1,000 camera. It doesn't make any sense. And the UI is, as we discussed, a big disaster. And I think it's really a big problem that we don't have as much contact with them. I think traditionally in the computer graphics community, we've always had good connection with the main industrial players, and this hasn't happened as much in computational photography. And this is really keeping not just the field, but also photography in general behind what it should be.
Do you have any idea why that's the case?
I have opinions. One of them is, I think, the hardware culture. I mean, these are, optics, mechanical engineering companies, and so all the levels of the hierarchy are occupied by people who think this way, and so thinking computationally is just not part of what they do. I suspect there are cultural issues. I mean, most of them are in Japan, and a lot of computation has happened more in the US. Although there's been a bunch of computational imaging in Japan as well, but just the companies have not embraced it as much. A lot of the stuff I really don't get. I mean, even if you don't go all the way to programmable cameras, camera manufacturers have been pretty bad at responding, to what their users want. Forget even, big, complicated algorithms and all this. But on the UI side, for example, photographers are pretty frustrated by some of the stuff that should be easy to do and is not. One simple example is, exposure used to be mostly about aperture and shutter speed, because changing the ISO meant changing the film, which was a big problem. But now that we have digital, ISO is as easy to change as everything. And it's taken a long, long time for manufacturers to make ISO as easy to change as the other one, and it's still not quite there. So we're not even talking about complicated, computational thinking. It just, there's a lot of inertia, yeah. And I think at this point, our best hope is that, I think a lot of computation is happening on the mobile, and mobile is really eating their lunch. The low-end camera market is dying. And hopefully the high-end is going to start freaking out and adopt some of what's happening on the cell phones, but I don't know, yeah.
Any advances on the opposite side of attaching professional lenses to?
I'll talk a little bit about it, not a lot about it. Yeah, let me give me 3 slides, I think. What can we do to sustain and improve the impact of the field? So here are a bunch of directions and areas that I think we should push more. I'm not going to talk much about deep learning because everybody's going to do it anyway, so nobody needs my encouragement. But here are a few observations and trends we should follow. First, the obvious, photography now is dominated by mobile phones. I don't know if you've seen this plot before, but this is a plot of camera sales over time, starting in the 30s all the way to the 2000s. Film took off and then didn't do as well. And then digital took over, went pretty high, and is not doing as well recently. And if you look at cell phone cameras, it goes really crazy, and you really need to zoom out. And even so, I haven't zoomed out enough. It's way, way higher than this. So today's cell phones are really dominating photography. And it's not just that every cell phone has a camera. People really use the camera. It's actually the main thing they do with their phone, not even talking. So what does that mean for computational imaging? So cell phones really create a lot of challenges in terms of form factor and power. And so maybe this will answer your question. So cell phones are really thin, maybe 7, 8 millimeters. And so if you think about a standard lens in traditional photography is 50 millimeter, and that's just the lens. We're not talking sensor and all this. So, shrinking things to fit on a cell phone is a big challenge. I've wondered for a while, why don't we have cell phones with multiple imagers? You put one wide angle and one telephoto, and people will, even if you have a discrete switch, I'd be happy to have this. And of course, the answer is, they already have a hard time fitting a 35 millimeter equivalent in the thickness of the cell phone. Apple got a lot of criticism for having the camera bulge out of the iPhone 6. So they already can't fit a wide angle in there, so the telephoto is an even harder problem. So what can we do about this? People have been proposing folded optics or various computational imaging solutions with multiple images. I'm on the scientific advisory board of this company, Light.co, that is building a camera that's reasonably thin and uses a lot of images in a creative manner. But I think that this form factor constraint creates a lot of pressure that can be relieved through computational means, and we should really be thinking about this. And power, on the other hand, also creates its own problems. If you start having multiple images, you're going to draw more powers. Processing time and power is a problem. Transmission is a problem, et cetera, et cetera. Of course, the other thing that characterizes cell phones is that they're connected, which is both an opportunity and a challenge, because as we said, transmission is expensive. And that's another thing where traditional camera manufacturers just have a really hard time thinking about connecting their cameras. And they're kind of trying, but I think that it's been pretty clunky so far. And people really expect to have all their data all the time on all devices and be able to do the same thing on their mobile phone or tablet than they do on the desktop, and this creates a lot of challenges. And finally, all this is going to be compounded by applications that try to have the camera always on, either for live logging or for health monitoring and things like this. How can you both deal with the power requirements? How can you deal with processing this vast amount of data? I think there's a lot of computational stuff that can help. Then we tend to focus on photography. It's in the name of the field, with computational photography. But in my opinion, video is really where the problem is. If you look at photography today, anyone with a DSLR and a little bit of work can take photographs that would have been considered professional 20 years ago. It's really remarkable. In the case of video, it's really not the case. It's really, really hard to create anything that doesn't look like crap. Footage is shaky, it goes out of focus all the time. Editing is a disaster. The software we have is super, super clunky. Selecting what to show is really difficult. So yeah, there's a lot of work to be done, and I think computation should be part of the answer. And really, I hope the field can help us, close the gap between amateur and professional video the way it's happened for still photography. And in general, scale is a big opportunity and a big challenge in computational imaging. How can we handle the huge amount of photos that people take? People don't even have time to look at all of them. You have more and more people thinking about photography as curation. It's not about pressing the shutter at the right time. It's about selecting good frames. And again, Pix is one example of an application that tries to help with this and extract good frames. I think we need a lot more work in this area, even more in the area of video than the area of photography. These days you have professional photographers who start using video cameras to take still images. So you have some magazine covers that were shot with a video camera. We just recorded, and later tried to extract that one frame that was the best. That's a lot of data, and so we need new visualization, we need new UI, maybe new learning algorithms to help people find the needle in the haystack. And the other scale issue that we have is, as deep learning is getting more and more popular and more effective, we need data to train it. And so getting, in a case like demosaicing, as I showed, it was kind of easy because you can get any photo degraded to simulate the mosaic problem. And here you have training data, even though, as I said, we had to do some extra work to find the relevant images. But for other cases, it's much, much harder to get data, especially as things get more subjective. What people like and things like this. So how can we gather this kind of data? And related to scale, I think that there's a need for a lot more systems research in computational imaging. The fact that people expect their data everywhere all the time, expect to be able to work from their web browser, really puts very different constraints on what kind of algorithm and data structure you can deal with. I was talking with people at Adobe. It's one of their big challenges these days, how to turn things like Photoshop into a web mobile application. Really, their data model just really doesn't work for this, and so they have to rethink the whole thing. Performance, as we discussed before, is a big challenge. So we need new compilers, we need new hardware, and we need compilers that map to this hardware. And there are lots of questions around software and hardware modularity. And I think that the model that we have with cell phone apps doesn't quite translate to photography, because usually an app is something that takes over your phone and does everything. It's very monolithic, it's in charge. But for my camera, what I would want is I would want to have different modules that work together all the time. And because photography is a real-time thing, these modules really have to interact. I want to be able to, take somebody's autofocus algorithm because it's nice and fast, somebody else's nice visualization because it shows me stuff that's useful for me, yet another person's automatic white balance. How do I make sure that all these things coexist, especially when they start accessing the hardware? If your autofocus needs to take images in order to judge whether they're sharp or not, but also your auto exposure starts asking for images to test if the exposure is okay, you have all these different components trying to access the hardware, and bad things will happen if we don't have good system solution. We also need to think a lot more about data structures to keep track of both the data and the metadata that's relevant to computational photography. For example, it would be very useful to track the noise level of images, the optical information for the lens, what algorithms the image has gone through, if we want to be able to have different software modules work together in a good, coherent manner. Similarly, what's a good way to store light fields that's going to be reasonably general for different sensor architectures and that will have all the relevant information. And really, if you look at the history of computer graphics, systems research has had a lot of impact on the way we think about the problems. If you look at OpenGL, at RandomMan, at a bunch of the ray tracing architectures, it's really provided not just a software framework, but also an intellectual framework to really think about different modules. And it's really helped people build on previous work in a really effective manner. I think there are lots of opportunities around hardware research, and both in terms of the sensors first. How do you build a sensor for a light field? Especially for high density light field, should it be the same as the sensors we have for 2D imaging? Probably not. You have a lot of challenges around, when you start shrinking pixel size as you're trying to gather angular information rather than just spatial. I think there's a lot of opportunity for on-sensor processing because we're talking about a lot of data. Can you find solutions to not send all that data? And even processing with the charge itself, not even just the information. So you have some really cool innovative sensors that can say, for half of my exposure, I'm going to integrate light that reaches this pixel, then I'm going to move it to the left pixel and start integrating to, at this new location. So you can do a lot of stuff directly with the charge that may allow you to embed computational imaging strategies directly on the sensor and allow you to gather better information. I think there's also a lot of opportunity around actuated photography. So I showed you the flash example. I'm very excited also about all these new camera stabilization systems. One of the big problems of video is really just framing and stability, and software stabilization and things like hyperlapse are one answer, but I think mechanical solutions are even better. And drones are another very exciting way to move cameras and light around. In past work, we've had a lot of fun putting a flash on a drone, and then the drone would follow the subject around based on where the photographer is to give you good quality lighting. There are really lots of opportunities there. Another example is, can we build good pan tilt cameras like these little guys, I guess, that can automatically supplement your filming. So maybe you're filming your kids playing and you want a different angle to make the video more exciting. You could put a camera on a tripod and let it be in charge of doing intelligent secondary shots. And the other type of hardware we should look into is computational fabrication and things like metamaterials. There are really cool things to do in terms of custom optics, in terms of even printing sensors. And really in optics, there's this new trend of building materials to really fine-tune almost at the atomic level how a given material interacts with light, so that you have a lot more degrees of freedom to decide where light goes, and it can really, I think, allow us to build lenses that are much more effective and much more cheaply. Photography is a deeply human activity, both when we take pictures and when we view them. And so I really think that there should be more research in these two areas. We need better UIs, both for the camera and for the software. We also offer, computational photography also offers new information, depth information, light field, what's the best way to interact with this, do people actually want to do these things? How do they want to interact with it? I think we need to understand this better. And I think that our research on new capabilities should be supplemented and informed by HCI research. And of course, photos are eventually seen by the human visual system, which has a lot of quirks and interesting characteristics. And a bunch of algorithms implicitly exploit this, but I think not enough. And I think there's a lot of room for new psychophysics, for example, new image metrics. So the metrics we have to compare to images are still really not good and still really don't match the human visual system. And this makes it hard for a lot of algorithms, both to assess them, but also to design objective functions when we work with optimization strategies. I think there's a lot of theoretical work that still needs to be done in computational imaging. There are lots of things we don't understand. What are the fundamental limits of what's possible? One example is we once derived a limit for depth of field. What's the best signal-to-noise ratio you can have if you want images between two different depths. And we designed some lens that tries to do as well as it can, but there's still a huge gap. There are like 2 orders of magnitude between the upper bound that we derived and the lens we were able to create. So does this mean that we need new theory to derive a tighter upper bound, or do we need to figure out different strategies? I don't know, but there's more understanding that's needed. And I think, in particular, computational illumination is also an area where we have very limited intellectual frameworks to think about what's possible. And related to this, it's surprising the scarcity of textbooks on computational photography. It's a fairly popular topic. There are lots of courses around, but there's maybe 1.5 textbook available. And I think this is really hurting the field, not just because textbooks are good to evangelize and teach people, but I think that they also force us to sit down and put everything we've done into a coherent intellectual framework, which I think, again, just like systems research, just like theory, is important to move the field forward so that we have good abstractions and good way of thinking about things. And I think we also need to broaden our horizon. We tend to think about photography as capturing what we see, but we should also think about capturing what we cannot see, something like superhero vision. And the motion magnification work we've done is one example, but there are lots of other things that I think we should push. Seeing beyond occlusion, visualizing non-visual properties. And if you're interested in the topic, I have a bunch of slides on my webpage that give a retrospective of all the kind of invisible things that humans have been interested over the ages, and what we should do to broaden this. And in general, I think that our limited impact also comes from our narrow thinking on photography, and that we should look into a lot of other applications such as robotics, virtual reality, inverse problems, scientific imaging, and especially for ideas such as computational optics, deblurring, and things like this. There may be very useful applications there because these applications have very severe physical constraints. We really try to squeeze out every single bit of SNR that they can, and I think computational ideas can really help. I think HCI is also a good area. Various input devices, barcode scanner, just try to get visual information, and they actually have really tight constraints to do so. And I'll conclude this by pointing out that pretty much a majority of sensing turns out to be optical, and so this is really a great opportunity for us. even when people try to measure things that are not visual, visual sensors tend to be a really good solution. For example, if you look at biology, they use a lot of tricks like fluorescence or diffraction and things like this to turn properties that they're interested in into optical properties that they can measure. Because at the end of the day, the two things we know how to measure really well are photons and electrons. And so, the big trick usually is to turn things into photon properties, and then we can measure them. And I really think that this creates great opportunities for computational photography to have an impact way beyond photography, but to all sorts of scientific and engineering endeavors. All right. I hope this talk will inspire you to look at some of these ideas and areas, and I'm looking forward to seeing your papers on the topic. Thanks.
We have time for questions. Why don't you write the textbook?
I know. I know I got myself in trouble because I'm also starting my sabbatical in September, so where's my excuse not to do it? I'll think about it. Yeah. I do realize I'm part of the problem. Yeah. Yes.
The work on motion amplification, can you do that with stereo views and better capture motion that's sort of towards and away from the sensor?
We cannot in the sense that we haven't done it, but this is something we've thought about because, we only capture the 2D projection of the motion for some applications. 3D is important, and so, either narrow baseline or wide baseline, multiple camera setups would probably be important for some applications, but we haven't looked into it yet. Yeah.
So I'm wondering a little bit if some of the problems we're having in terms of advancing the field and making things, delivering things to real people is maybe we're so far ahead of what typical users understand. And there's been so much progress lately. I'm wondering if you have any thoughts on that. If maybe that's at the root of the problem. It's just like I imagine trying to explain some of these things to my mother, and I'm just not getting very far.
Well, part of my answer is that this is why I say we should have more research on HCI. So we can do a lot of stuff computationally, but we need to understand better what people can handle and how they want to interact with things. Things like light field, for example. People don't need to know about light fields and things like this. But the question is which capabilities are useful to them and how do you need to expose them and things like this.
If people have a good sense of what makes a photo good.
No, some people have opinions. Does it matter? For some things, yes. For some things, no.
I think people have when they see something they like, they know it, right? Yes. But whether that's good and whether you can measure that that's good and whether that's good in some uniform, objective way.
Something that they shot. Yeah. Not like some random photo.
No, I think so.
Well, certainly, one of the challenges that the field has also is that people have very low standards.
Right. I think that's what I'm getting at.
Yeah. And it's a good question. And people will see the difference when you show them. Pics is an example where, I see a lot of photos on my Facebook feed that people say, oh, I saw so-and-so, and you see the photo, and the person is so backlit that I cannot recognize who it is. But yet, they're excited to share this photo with the world, and we have some things we can do to make this better, and people would notice, but will they notice enough that they'll care is a good question. It is one of the challenges. I think, but to go back to your question, I think some of it is natural that research should be years ahead. There's a famous curve about innovation that looks at things like the internet and how long it took from the lab to actual deployment, and we're talking about decades. It's not like 6 months. So some of this is natural. It doesn't mean that we should say, oh, this is okay, our stuff is not applied just because we're geniuses who are not understood in our own time. But I think we should try to push them to to become useful and to understand why they're not useful yet. I think, yeah, there are a bunch of examples in the field. I mean, light fields are one of them where we need to do a little more thinking about what would make light fields useful, what are the parameters, how to expose it, and things like this.
I think that specifically in this area is actually a layman can understand what he's getting. They say wow when they're looking at the videos coming out of the papers, which they won't say about the theoretical physics paper. But the difference is whether you can do things easily. Think of panoramas that were out for 20 years, but now people can just press a button and take it.
Yeah.
Suddenly it's possible, and people do that. Wouldn't have done before.
It's also a question of finding who it's useful for and things like this. So in the case of light fields, I think that at least at this point, it's mostly advanced users who will benefit and care about it. And of course, there are, well, and the other problem, as usual, is also just engineering, market, and things like this, and how to get out of local optima. I think that, I mean, again, to talk about light field, I think that with today's technology, we could build a DSLR that has a light field sensor that would be really compelling, that would have good refocusing, zero resolution loss, and things like this. There's no fundamental problem with it. I mean, if you take a full frame sensor, you scale it to the 1.3 micron pixel size that people have in cell phones, you get a great light field camera, and there's no fundamental problem there. But one big issue is how do you get people to manufacture this sensor for you, and how do you get a market that's big enough, and how do you go through all the increments that really take you to the same level that you had with your same DSLR, just because the DSLR has been optimized to death through the years. So I think there are also challenges like this. Yeah. Yes?
Your slide about putting multiple sensors in the cell phone and kind of everything being too thin. Do you think that there's any chance that we can convince somebody like Apple to come up with a separate, like they have the 6 and the 6 Plus, like 6 good camera edition?
Well, there's a lot of rumor going on around the 7. Some people do claim there will be a special camera. I personally don't believe
this
it.
is too thin for me now. Like I just doubled the thickness of it with adding a case. I would much rather add a camera. But we don't do
I don't have any visibility over what Apple may be willing to do or not. I think that the fundamental problem, again, is that people don't care enough for Apple to sacrifice the thickness.
Well, I think your local minimum point is good too. Is that they drove, or local optimum. Thickness has been this obsessive factor for some.
Ridiculous.
Just like megapixels were an obsessive factor for camera sensor. And it's really hard to dislodge that, right? And say, okay, it's going to actually
be a camera and a big battery.
And they did do that. There was an iPad that was a tiny bit thicker than the last one, and it was huge.
Well, as I said, I mean the bulging camera on the iPhone 6 was a big negative PR for them. So I think I don't know that I'm super optimistic about this, and you have people trying to have add-ons like DxO has this little. I don't remember if I have it. DxO has this little thing that you can add to your phone. Oh no, I didn't take it with me.
The little thing. Suppose you had a DSLR right now.
Yep.
It looks like a DSLR. It's same weight and same lenses. You just put your phone in as the interface and the CCD.
Yeah. Sure.
Would you have bought that?
Yeah. Probably, possibly. I don't know if it's the best combination. I don't have super strong opinions, or if
Sony sold.
I mean,
that for a while, right? That was the.
Yeah. So Sony had this big.
It's an interesting device. I think it was Sony, right?
But I think it was smaller than DSLR, right? I mean,
Yes.
the Q1.
But it nicely decoupled the UI from the optics.
Yeah, and DxO has this product too that does something like this. But I think, you're talking about something different. It's like, let's not try to have a small add-on to the phone. Let's just take the big SLR and make it talk more to the phone. I think this needs to happen. I don't know what the good. I don't know what the good solution is, or if it just I mean, I don't understand why you don't have more cameras running Android, for example. There has been a couple of examples of people kind of trying, but not really. I just don't get why people are not pushing it. And I think that's a little sad. I mean, if you think about it, when digital happened, the camera industry made some big changes, right? They were willing to take very big steps, and they changed a lot of stuff on the camera, and now this is over. They're really just stuck in another local optimum. Yeah. No, I mean, and I think in the future you will indeed probably have a situation where you'll only have cell phones, and that'll be the default camera, and you'll have big cameras for serious people and professionals, just because the DSLR size is a really good form factor if all you're doing is photography. It really fits well in your hand. You have a lot of control. You can put better physics in it. So in my opinion, you'll always have something this size just because it's very convenient. And if you're really seriously into photography, you don't care carrying something like this. So there will always be something that big. I don't know what that thing will look like exactly, but yeah. But it's probably going to be this very bimodal market. Maybe it will be, maybe not. Yeah, no. I mean, there are interesting questions also about this super high resolution imaging, and then you do everything as a post process and stuff like that. I suspect. I mean, there's still a lot of value in focusing light optically. It's really effective at getting sharp images, so I suspect that some of this will always happen. But for other situations, maybe there'll be more generalized, wide angle and more directional information. Yeah.
All right, well, let's
Thank you.